Today we're going to talk about the three fundamental kinematic equations that describe motion in physics. We're going to start with velocity. If I want to find some final velocity after a period of time, we can always start with any initial velocity that I might possess, and then add on a change in velocity. Recall that from an acceleration versus time graph, we can find the velocity just by taking the area under the curve. So here it's a rectangle. It's pretty easy. If I want to find the area of the rectangle, it's going to be base times height, which is a times t, and that is going to equal any sort of change of velocity. So our first kinematics equation says velocity final is equal to any velocity initial plus acceleration times time. This is our first kinematics equation. How about displacement? If I want to find the displacement, we can start with any initial displacement that we might have, and then add on a change in displacement. Well, recall that from a velocity versus time graph, we can find the displacement simply by taking the area under the curve. So here we have a rectangle, velocity times time, base times height, and that is going to equal any change in displacement. So let me add that to our equation here, plus vt. Now, suppose this is just an initial velocity. I'm going to add an I there, and suppose that there's a change at some point. What if we increase? What if we accelerate? Well, now it becomes a little bit more complicated, because now not only do I have a rectangle to find the area of, but a triangle as well. I got to find the area of this guy here, and then also this triangle. So we can do that, right? We have a little v up here. We can do 1/2 base times height to find. We got a t down here. We can just do 1/2 base times height to find the area of that triangle. I'm going to write it down here. The area of the triangle up there, in other words, the change in velocity, would be 1/2 base times height, 1/2 bt. And that's fine. We can do that. But this v right here tends to be hard to come by. Any change in velocity is not always readily available. At least not as readily available as, for example, the value of the acceleration might be over that short period of time. So let's take a look at the AT graph. So for that moment in time, for that triangle over there, the increase in velocity, the acceleration curve would look something like this. And we can find the area under that curve to obtain that value of velocity that the arrow is pointing to. That's not always so readily available. So let's look back at our equation here to calculate the area of that triangle. And instead of doing 1/2 vt, I could do 1/2 at times t. Now all I did here was I substituted the value of velocity here using the area of my AT graph. So instead of velocity, I'm using acceleration times time, which is the same thing. We have two t's here at the bottom. We're getting a little bit jumbled up in space, aren't we? We have 1/2 at times t, which simply reduces to 1/2 at squared. And now that is a measurement of displacement. So I'm going to add that onto our master equation here, 1/2 at squared. And now here we have it. Kinematics equation number 2. I'm going to rewrite the equation that we just derived. Change in displacement is equal to any initial displacement plus velocity times time plus 1/2 at squared, reflecting any change in velocity. And then also our first equation, we had any final velocity is equal to any initial velocity plus acceleration times time. If we solve this equation for t and then substitute it into this big old scary equation right there, we can come up with a third equation that actually proves quite helpful. And that equation is the velocity final squared is equal to the velocity initial squared plus 2a delta d. And this is our third and final kinematics equation of physics.